Hi everybody. So today we're going to be starting on arc length. Alright, so arc length. What we want is going to be to grab any function that we're given, so long as the function is continuous on some interval and it must be differentiable on that interval. Alright, so on the screen here I have some axes, some x and y, and I have some function, generic function f of x. And what I'm going to do at this point in time is I'm going to put this on an interval, call it from a over to b. Alright, now given that this function is on an interval, what I want to do then is I want to start subdividing. Alright, and the reason I want to start subdividing is because I want to be able to calculate this specific section of length between the interval a and b for this function f of x. Alright, as you notice, from a to b it goes up, then it goes down, and then all the way back up to this point. So we want to figure out a way to partition this to make things a little bit easier to handle. Alright, so what I'm going to do right now is I'm going to start breaking apart this specific interval. Alright, so follow me along with that. Alright, so here's my interval from a to b. I've partitioned it. And what I'm going to go through here is this is going to be x sub 0 or x naught. This is going to be x sub 1, x sub 2, x sub 3. X sub 4. Alright, we'll go skip a few here and we'll go to x sub I. Alright, perfect. And this will be x sub I plus 1. And then after that we'll skip a few and we'll say this is going to be x sub n minus 2. This will be x sub n minus 1. And finally this will just be x sub n. And what we're going to do is we're going to do the same thing as we did back in Calc 1, that we're going to start defining our delta x's just to be the subdivision of the interval b minus a by some value that we choose just to be n. Alright, now what I'm going to do after I've done this is I'm going to start creating these points in accordance to the outputs of the interval that I was looking at with the actual function itself. Alright, just like this. And again, the reason I want to do this is because, again, eye on the prize, I want to focus on the arc length of this function from the interval a to the ending of the interval b. Alright, and what I'm going to do now is I'm going to start labeling some of these points up here. Alright, this point, let's call this point P naught, let's call this point P1, then P2, then P3, P4, this will be P sub I, this will be P sub I plus 1, this will be P sub n minus 2, P sub n minus 1, and then P sub n. Alright, just making sure that I label my points. Once I have that, what I'm going to do then is I'm going to start creating some of these lines between these specific points. Alright, so here we go. I'm going to create this line here. There we are. Alright, that's my first line. I'm going to go through and I'm going to make the second line just like this. Alright, and I'm going to keep doing this for every single point. Alright, so follow me along as you're doing this. Alright, here we are. So what I did is I just filled in all of the lines that are going to be connected from all the subsequent points that we were defining. Alright, now as you're going to notice, look at this line from P2 to P3, then look at this line from P sub I plus 1 over to P sub n minus 2. These lines kind of look like they almost sit on this function. Now there is an issue with this, that these pink lines here are straight lines versus the function, it's more of a function that has some sort of curvature to it. Alright, So one of the things that we then want is we then want to find a method to then start shortening these line segments so that they'll be a little bit more accurate. All right. So before we get to that, all right, one of the things that I wanted to state on here was the items that we were working with, all right, or the restrictions. F of x is continuous on the interval from a to b. All right. Now, f of x must also be differentiable on the interval from a to b. And that's non-inclusive. Because again, remember, in order to be differentiable, you don't necessarily need to exist at the endpoints here. All right. Now, when we're observing this is going to be real nice, because what I want to do is I want to calculate the distance between two of these points, because calculating that distance kind of gets me the measurement for that specific line segment. All right, so I'm going to be looking for that. I'm going to calculate, or I'm going to find the distance, and I'm going to say between 2 points. Call it P, for simplicity here, let's call it between P3 and P4. All right, so I'm going to want notation-wise. How are we going to look about the, or how are we going to think about this notation-wise? All right, so the notation here, I'm just going to denote as, it kind of looks like the absolute value here of P sub 3 with P sub 4. All right, I'm looking at the distance between these 2 points. All right, so looking at the distance between these 2 points, well, what we can do is we can use the distance formula. Using the distance formula, we're going to take the difference in the x-coordinates. Well, the difference in the x-coordinates for P3 and P4 is just x4 minus x3. Like such. And we're going to square it. And then the difference in the y-coordinates. Now, the difference in the y-coordinates, we really don't have the y-coordinates at this point in time. However, what we can do is we can say, well, P4, point number 4, is going to have some x-coordinate of 4 and some output, let's call it y output, that is going to correspond with that index. Same thing here for P3. Is going to be some x3 comma some y3 that we observe. In a later time, we're going to insert the y values for the f of x's, and then we'll see how they hold. All right, so in here, again, the distance here, x4 minus x3, and then y4 minus y3. Square it. There we are. So here's the distance formula. Now, that's all fine, that's all great, because this actually answers a lot of our questions. All right, one of the questions that it answers is that x sub 4 minus x sub 3, x sub 4 minus x sub 3, what's that distance? Well, that's delta x. That's how we defined it from the beginning, which means x sub 4 minus x sub 3, that's just delta x squared. Plus y sub 3 minus y sub 4. That's not exactly a specific value that we've defined yet. All right. So what I'm going to do there really quick is I'm actually going to hold on to that, and I'm actually going to see what I want that to be. All right. So I'm going to substitute here delta y, because this is going to be some change in the y values. All right, now if it's going to be some change in the y values, then I want to hold on to that. And what I'm going to do is I'm just going to call this delta y, and we're going to make this delta y sub 4. and that's going to be squared. Just like that. All right, and there's a reason why I want to do this. The reason why I want to do that, and I'm going to go on a little side note over here on the right-hand side, the reason I want to do that is more because of this. I'm going to use the mean value theorem from Calc 1. So the mean value theorem from Calc 1. Well, the mean value theorem says that we must be continuous, we must be differentiable on some given interval, which again, by the beginning, we are. And so what we then want to do is we then want to identify what interval we're working with. Well, the interval that we're working with, that's the interval from x3 over to x4. All right, that's the interval that we got. So the mean value theorem is then going to guarantee that there is some value in here that when I take that value and I put it into my function, it will give me the same slope as the slope of the endpoints. All right, so given this interval on this function, I know that there exists, so I'm going to say there exists a, let's say, x sub I star, and this is just some random sample point in this interval, in the interval, all right, and actually I'm going to go back and spell it out. In the interval x sub 3 comma x sub 4, on that interval, such that f of x sub 4 minus f of x sub 3 divided by x sub 4 minus x sub 3 is equal to the function evaluated at x sub I star. All right, so that's what we get from this particular piece. Oh, excuse me here, this is a derivative. My apologies, because it's supposed to be the derivative that's equal to the secant line. There we go. So now that I'm looking at this and I see that implementing the mean value theorem will get me this result. And this is the result that I want right in here. All right, because in this result, what I can do is I can say, well, this is just some output. But isn't the output, the f of x sub 4, just some y value? Sure is. Which means, at this particular time, shouldn't this just be some delta, call it y sub 4? Yeah, it sure is. Well, that's going to be divided by this piece right here, which, as you would agree, that's just delta x. And it's going to be equal to the derivative of the function evaluated at some x sub I. Now, that's going to be awesome because, once again, this now is going to imply that delta y for that specific interval in here is going to be equal to f prime of x sub I star multiplied by delta x. Which means, do we have a substitution to make? Yes, we do. We have a substitution now that we can make. And this substitution is now going to say, okay, well, you know what, we were initially working with this delta x squared. Oops, excuse me. Delta x, there we go. And that's going to be squared plus this new piece that we just found. This is now going to be f prime of x sub I star multiplied by delta x. And then we're going to square that result. There we are, just like that. And what you're going to notice here is that both of these individual terms contain a delta x, which means we can factor out that delta x squared, And we're still going to be left with 1 plus f prime of x sub I star squared. Now, delta x, the way we define delta x is largest number minus smallest number, which means it's always going to be positive. So naturally, when we think about this, we should get the absolute value of delta x when it's evaluated with the square root. And then we're left with 1 plus f prime of x sub I star, all that squared. Just like this. All right, looking good so far? All right, so all we then have to do, oops, excuse me, I factored this out wrong incorrectly. There is no, my apologies. The square is only on the f prime because we've already distributed the x squared. My apologies, everybody. Here we are. All right, that's the square root of 1 plus this quantity is just f prime of x sub I star quantity squared. There we are, just like this. Perfect. And then after that, we talked about this absolute value of delta x. The way that we define delta x is that it's already in itself just positive. So this is just 1 plus f prime of x sub I star, and there we are, squared, and there we are. So if we wanted to find this arc length, between P3 and P4, that arc length, this line segment here, would have this given value, which if you look at it, that given value only depends on the delta x that we would be able to find and the derivative of the function. So now, imagine, let's say that we don't just want to approximate this, right? Because as I have it here, it's just an approximation. What if we want more than an approximation? What if we want an actual exact length? Well, if we want an exact length, what we're going to have to do is we're going to have to take a whole bunch of these individual values and we're going to have to cut them up into smaller and smaller and smaller increments. In other words, we need to apply the Riemann sum process. So, how does that look like then? Well, what I want to do here is I want to take the limit as n goes towards infinity for the summation of all of my indices, starting at 1 going over to n, for all of these individual line segments, which is 1 plus f prime of x sub I star squared delta x. I'm going to take the summation of all of these subdivided by n, and then I'm going to infinitely subdivide those intervals. In other words, all of these line segments are just going to get smaller and smaller and smaller so that they each individually fit on this line. And therefore, it's going to measure that line because, again, we're taking the summation of all of these individual segments. Now, that looks awesome because at this point in time, this is your Riemann sum. It's the Riemann sum, and the Riemann sum, according to Calc 1, well, we can express that as the interval from when we initially started, from a to b, and the function that we're looking at is the function right in here, which is just the square root of 1 plus f prime of x quantity squared, and then that delta x just becomes our dx. Which means, can we find the arc length of this function? And the answer is yes. Yes, we can. All right. So let's go ahead and let's formalize this a little bit more. So what I'm going to do is I'm going to summarize this and give you a nice little recap of what it means. So arc length formula. All right, here we go. So this is going to say if f prime is continuous on the interval from a to b, then the length of the curve y is equal to f of x on the interval from a to b is this arc length, the interval from a to b, multiplied by 1 plus f prime of x squared, and then take the square root of that with respect to dx. Alright, so this is the formula that we're working for arc length. Now, could we have gone back and could we instead, let's say this function was not a function, let's say this function was actually a relation, meaning an equation that does not pass the vertical line test when it's graphed. Could we then interpret this in terms of y values? Sure. According to Calc 1, we could just reorient, and we can take the integral from c to d, and this will just be 1 plus some function that's defined in terms of y values squared. And instead of dx, well, we're going to do this with respect to dy. That's all there is. All right. So now let's use this newfound function, or this newfound formula, to extract a few arc lengths. So on here, we want to find the exact length of the curve. So notice it says exact length, which means we do not want an approximation. So no approximations needed here. All right, so let's go through. This is going to be 36y squared is equal to the quantity of x squared minus 4 cubed. And this is going to be for the x values that are bounded between 2 and 3. And y is greater than or equal to 0. Awesome. All right, so let's go through and let's see if we can try to extract some sort of function here. All right, so trying to extract some sort of function here. Let's see if I can go through and if I can solve this piece here. So I want to solve this piece. Let's see if I can solve it for y. I can either try to solve for y or I can try to solve it for x. At the end of the day, doesn't matter. All right, so let's go through. Let's solve for y. I think y might be a little bit easier to work with. All right, so if I solve for y, this is going to be x squared minus 4 to the power of 3 divided by 36. And then, I'm sorry, that's still y squared, which means that y is going to be positive or negative, and I'm going to take the square root in here, and that's going to be the square root of x squared minus 4, quantity cubed, all divided by 6. There we are. Perfect. All right, so now that I have this, I can then go through and then I can start extracting. How do I want to set this up? Do I want to set this up with respect to x or with respect to y? All right, naturally it looks like I solved for y, which means I kind of want to use the y values to find some sort of interval here, or some extraction here. All right, one of the things that I got to worry about is I got to worry about the domain here. So really quickly, I'm going to do this here. I'm going to say investigate the domain for the square root of x squared minus 4. And the reason I want to investigate that domain is because this domain is going to give me insight as to what values I'm going to be able to use. All right, so that domain, x squared minus 4, must be greater than or equal to 0, because we can input a value of 0, but other than that, they need to be positive. So then this factors into x minus 2, x plus 2 must be greater than or equal to 0. Awesome. Which then tells me that I need to break up my domain, or my values, in between two of the values. All right, the first value being -2. So the first value being -2, and then the other value just being 2. And then I'm going to go through and test some values. All right, so I'm going to choose 0 in here. So choosing 0, I'm going to plug 0 in here. 0 minus 4 gets me -4. -4 is not greater than 0, which means this does not work. So the interval between -2 and 2 does not work. That is not a part of my domain. All right, now this process, what they gave me, went from 2 to 3. So let's see, from 2 to 3, will that work? All right, well, let's choose some value in here. We could choose 2.5, we could choose 3, 4, 5, whichever it may be. Let's choose 3 for simplicity. 3 squared gets us 9. 9 minus 4 gets us 5. 5 is definitely greater than 0, which means that works. Naturally, since this is a square root of a parabola, then this side will also work as well. All right, perfect. So the domain that we're working with, x is between 2 and 3, it will work for what we need. So we don't need to go through and we don't need to solve for y's instead, or solve for x's instead. We're actually perfectly content working with this piece of information here. So which one am I going to use? Am I going to use positive or negative? Well, that's where this value comes in. We're going to use the positive version because y is greater than or equal to 0. So the function that we use, f of x, in other words, this is the y value, is the square root of x squared minus 4, oops, like such, raised to the power of 3, divided by 6. And again, we're using the positive version because of this restriction. All right, so we can now start trying to take this derivative. And let's see if I can rewrite this a little bit cleaner. That's 3/2 divided by 6. There we are. So let's take that derivative. Let's find f prime. All right, so my derivative here. My 6, that's just going to be a constant, so I'm going to carry that 6 of a constant. What I'm going to do is I'm going to drop the exponent forward, so that's going to be 3/2. All right, and that 3/2 is going to multiply that function itself. That's x squared minus 4, and then I subtract 1 from the exponent, which now means I have 1/2. All right, perfect. And then I multiply by the derivative of the inside. The derivative of the inside is just 2x. There we are, applying the chain rule. All we have to do now is just clean it up. All right, so let's see, 2 divided by 2, that's going to cancel out, and then 3 divided by 6, that's going to factor out to 1/2. So in here I have 1/2 multiplied by x. All right, good so far. And then that's going to be multiplied by x squared minus 4 raised to the power of 1/2. There we are, not bad. All right, so to find the arc length, so now the arc length. The arc length that we're going to be looking for, or that we're going to be working with, is going to be the integral between 2 and 3, because we're doing this all with respect to x. And this is going to be 1 plus, or sorry, square root of 1 plus f prime. F prime is that 1/2 x multiplied by x squared minus 4 raised to the power of 1/2. That's going to be squared. And this is all with respect to dx. All right, I know it looks kind of intimidating, but I can guarantee you now is when we actually start working with the calculus portion of it, which makes it really nice. So that's the integral from 2 to 3, and this is going to be 1 plus, this is going to be 1/4, that's going to be x squared, and then the half here of the exponent is going to cancel there, which means we're left with x squared minus 4 as well. And that's all inside of the square root with respect to dx. There we are. All right, looking good so far. I like the way this looks. All right, so let's keep going. This is going to be from 2 to 3. Now, as you're going to notice right here, a lot of this material doesn't look like it's going to factor or anything, so we got to get creative here. All right, and by getting creative, this is what I mean. what I'm going to do is I'm going to factor out a 1/4 from this specific radicand. All right, so I'm going to factor out the 1/4 because what I want to do is I want to get rid of the fractional terms. All right, which means I'm going to have 4 plus x squared multiplied by x squared minus 4. There we are. Just like that, and that's all dx. Now, square root of 1/4, that's just 1/2. So that's 1/2, and then this is going to be 2 to the power, or sorry, from 2 to 3. And then this in here, inside of the square root, is just going to be 4 plus, this is going to be x to the 4th minus 4x squared. Just like that, and that's all dx. Now look at this piece right here. X to the 4th minus 4x squared plus 4. I believe that is a perfect square trinomial. Is this just x squared minus 2 squared dx? And if you want, you can again take a minute to look at that. So that's a perfect square trinomial. And again, you can go through and verify. Well, let's verify here. The first term squared, so that's going to be x to the 4th. There we are. Second term is going to be this multiplied by this. So that's x squared multiplied by -2. So that's -2x squared doubled, which is 4. So -4x squared. And then the last term squared, which is just 4. Perfect square. Awesome. All right. Well, if it's a perfect square, now all we have to do is evaluate this. But this piece of information here, if we're looking at x is equal to 2 and x is equal to 3, then this function will always be positive, so we don't need to worry about the absolute value. This is just going to be x squared minus 2 because the square root will cancel out with the 2 without needing the absolute value. Look at that right there. That turns into a Calc 1 problem. Yay! Calc 1 problem right there. Which means now we just take 1/2 multiplied by, and let's see, this is going to be 1/3 x cubed minus 2x evaluated from 2 to 3. And all we have to do then is just evaluate that. All right, so let's go through. Let's go through and let's find that evaluation. 1/2 multiplied by 1/3, and this is going to be 3 to the power of 3 minus 2 times 3. Perfect. And then we're going to subtract out 1/3 times 2 to the power of 3 plus 2 times 2. We're going to simplify here, so it's going to be 1/2. And then this is just going to be 9, because that's 27 divided by 3, so it's going to be 9 minus 6. And then this is going to be 8/3, so it's going to be minus 8/3, and then plus 4. There we are. It's looking pretty good. So 9 minus 6, that's going to get us 3. And then we're going to do 3 plus 4, which will get us 7. And then 7 minus 8/3, that should get us 13/3, which means this is just 1/2 multiplied by 13/3. In other words, this is 13/6. And there's your answer. Nice. So we found our answer, and the answer, that arc length, is 13/6. Awesome. So again, when we're looking at this, one of the first things that you have to do is you have to identify, do I kind of want to integrate this with respect to x or with respect to y? All right. We kind of identified that we wanted to do this with respect to x because it would be easier to solve for y in terms of x. All right. Now, let's see another example using this technique. Oops, excuse me. This is part B. So for part B, we're going to do x is equal to y to the 4th divided by 8 plus 1 over 4y squared. And this is going to be for my y values being bounded between 1 and 2. All right, so let's take a second, try to dissect this, and then I'll get back to it in just a bit. All right, so here we go. Now, from what I'm given here, all right, so I'm given a function of y. All right, and again, this is not a function of x because this will not pass the vertical line test. And also, I am given these y value bounds. So the interval is for y values. All right, now since this is the case, more than likely what I'm going to be doing is I'm going to be using arc length in terms of the function that has y embedded into it. All right, and this is going to be dy. So naturally what I then want to do is then I want to take this derivative for this function, which is, in this particular case, g of x. So I'm, not g of x. So in here, what I'm doing is I'm setting this to be g of y, and this is my function x. So x is g of y, which is y to the fourth divided by 8. And I'm going to say this is going to be plus 1/4 multiplied by y to the power of -2, just to make things a little bit easier. Now, when I do this, I can then take the derivative, so this is going to be g prime of y. So take the derivative here, drop the exponent forward, so that's going to be 1/2 multiplied by y to the power of 3. Drop the exponent forward, that's going to be -1/2 y to the power of -3. Perfect. Now what I want to do is I want to square this result, because what I'm going to do when I square this result, I'm going to be able to plug it in directly. All right, so at this point in time, I'm just going to do g prime of y, and I'm going to make sure I square this. So this is going to be 1/2 y cubed minus 1/2 y to the power of -3, and this is all going to be squared. Perfect. All right, now using this whole arc length formula, I'm going to say my arc length is going to go between the y values of 1 and 2, and then I'm going to have 1 plus this specific piece, which is just 1/2 y cubed minus 1/2 y to the power of -3 squared. And this is all dy. Nice. So let's go through and let's expand this, and then we'll go ahead and we'll add it to that 1 that we have here. Alright, so this is going to be from 1 to 2, and I want to expand, and the reason I want to expand is because this doesn't look too nice right here. So I want to expand it to see if we can make it look nicer. Alright, so let's expand it. So this is going to be 1/2, and that's going to be y to the power of 6, and the next one's going to be minus this times 2, which is just going to be 1/2, I believe. So that's 1/4 multiplied by 2, that's 1/2, yep. Y cubed times y to the -3rd just gets me y, or y to the power of 0, which is just 1. And then I have plus, and then this here, oops, excuse me. I made a fudge. This first piece should be, in this particular case, 4th. There we are. Because this is now 1/4 y to the power of -6. That's dy. And this is all underneath that square root. Just like that. Perfect. Alright. Let's go through and let's add some terms together. So this is going to be 1/4 y to the 6. 1 minus 1/2. That's going to get us plus 1. There we are. Oh, sorry. Cheese and crackers, plus 1/2, there we go. And then we have plus 1/4 y to the power of -6, and that's all inside of this square root dy. Now looking at this integrand, again the integrand doesn't look nice. So we got to kind of get past that reasoning of something being nice in this particular case. Alright, so what I'm going to do here is I'm actually going to notice that this is a perfect square. It is a perfect square trinomial. which is awesome. Now, the fact that it's a perfect square trinomial, maybe it's not something that we can see directly, but let's look at this. If I take the first piece here, and if I consider that 1/2 y cubed, and if I consider this second piece to just be, let's say, 1/2 y to the power of -3, and I square all this result, do I get that individual radicand? Well, let's see. Square this individual piece, we get 1/4 y to the 6. Square this individual piece, we get this here. Okay, it's looking good so far. Now, take this times this, and that's going to be for the middle term, and double it. This times this is just going to be 1/4. Multiplying y cubed times y to the -3 just gives us 1, because that's going to be y to the power of 0. So 1/2, double that, so 1/2 times 2, or sorry, 1/4 times 2. 1/4 times 2 just gets us 1/2. So it is a perfect square. Now, we're going to be allowed to use or to cancel out the square root with the square, because on this given interval from 1 to 2, the y values are always going to be positive. Which means all we're really looking at is the integral from 1 to 2 for 1/2 y cubed plus 1/2 y to the -3 dy. That's all that we have to look at. Which is really nice because, again, this now turns into a Calc 1 problem. So let's work with that. 1/2 y cubed, so that's going to be what, 1/6 y to the power, oops, excuse me, not 1/6, cheese and crackers. Alright, so this is going to be y to the power of 4, so that's going to be 1/8, there we are. And this is going to be minus, we're going to add 1 to that exponent, so adding 1 should be a -2. And then we're going to divide by that new denominator, or that new exponent. It should be -1/4. Alright, perfect, because if we take this derivative, negative times a negative becomes a positive, 2 divided by 4 becomes 1/2, and subtract 1, perfect. So that just becomes from 1 to 2. So evaluating this, that's 1/8 multiplied by 2 to the power of 4 minus 1/4 multiplied by 2 to the power of -2, and then minus 1/8 plus 1/4. Alright, we should be able to get a value of 33/16. Really nice, really awesome. Great. Alright, so now that we have this, we now have more to talk about when we're looking about arc length. Alright, so there's going to be a different problem here. So problem C, we still want to find the arc length of this function, but now we're working with hyperbolic cosine. Now, hyperbolic cosine, that's one of the functions that we ended up talking about in Chapter 6. So if you need a review on hyperbolic functions, go ahead and review Chapter 6. That way we can see what we're looking at there. Alright, here we go. Alright, I'm given a function here, so I'm going to call this f of x. It's a function in terms of x. Hyperbolic cosine of 2x, there we are. And they're giving me the interval on the x values. So all of this is kind of hinting at me to use this formula, which is 1 plus f prime of x squared. It's hinting me to use this formula here with respect to x. Alright, which means I need to go through and I need to find this derivative. So what is f prime of x? Alright, well f prime, if you remember these derivatives, that's going to be 0, and then the chain rule here, so that's going to be 1/2 multiplied by 2, so that's just going to be 1 multiplied by hyperbolic sine of 2x, just like such. Alright, so awesome, looking pretty good so far. Now all I have to do is arc length, evaluate from 0 to 1. This is going to be 1 plus hyperbolic sine of 2x squared. And that's going to be the square root of that. and that's all going to be with respect to dx. All right. Now, what I'm going to have you all do is I'm not going to work this example out for you all. You're going to have to keep working this example on your own. And what I'm going to have you do is I'm going to have you post up your answer on the discussion board. All right. So when I ask for the discussion board answer, it's going to be in regards to part C for this example. All right. I just want to see what is that final result. All right. So what you can do is I will leave the option open that you could submit a picture of your work. And so all you would need to do is just finish this example and then upload that work to the discussion board and you'll have your credit. All right. So that's part C. I'm not going to give you an answer for that. I'm just going to let you guys find that. All right. Now for the next part, we want to build what is known as this arc length function. All right, so this arc length function is going to be a function that is going to be built upon finding the arc length. And this should be for any given function that we are given. All right, so the arc length function, we're going to denote S as the arc length. So this is going to be S of x. And this is going to be the integral from a to x of 1 plus f prime of t squared, squared, and this is all with respect to t. There we are. So when we start looking at this, we can start going through and we can start identifying what will be this function that we're looking at here. Now notice I'm using different parameters here. I'm saying my function f, whatever is given to me here, I'm just going to interpret in terms of t. All right. Given that interpretation of t, I will then be able to set an upper limit parameter as my stopping point. So what that means curve-wise is this, that if I'm looking at some random function, and let me build this upon this way, there we are. All right, there we are. Let's hide that. Perfect. So what we're looking at here in this particular piece is that this is going to be with respect to x, and that's completely fine. All right, so here's going to be the function. Here's f of x, or we can actually call this f of t if you'd like. Make things a little bit easier. There we are. Now the arc length that we want to look at, the arc length is going to be starting at A, and it's going to be going over to B. Now, typically that arc length is going to calculate this specific length right in here in green, as we see from before. Now, what if we don't want to identify the stopping point? What if the stopping point now becomes more static, right? Or sorry, more dynamic. It starts moving. So what I'm going to do is I'm going to just classify this as x. And x can move either, oops, wow, that was very, very bad. X can move either in this direction or x can move in that direction. All we know is that x is going to be its stopping point. And that's what this arc length function does, is it's taking this upper limit and it's now saying, hey, I'm not going to fix that upper limit. Now what I'm going to do is I'm going to have that upper limit just move up until some x value. Given that, if this x moves to the left, then that arc length is going to be smaller. And this will be able to calculate what is that arc length without having to do the original calculations like we were doing before. If this x moves to the right, closer to B, then automatically this arc length, well, it's going to start getting larger. So again, this method now allows us to start thinking about making our parameterizations for this arc length function in terms of x. Can we then build a function out of this? And the result is, yes, we definitely can. All right, so here's an example to this. And the reason I say this, and the reason I want to focus on this, is because when you move on to Calc 3, you're going to be doing this process quite a lot, where you're going to be able to parameterize a given function in terms of t, not necessarily in terms of x. Now, when we do this, we often like to think of t as, let's say, a parameter that is considered as time, which means could we then parameterize instead of x's in terms of t? And yeah, we sure can. Starting with, with starting point. There we go. Sorry. I'm trying to talk and write at the same time, and it's not faring well for me. Here we are. Perfect. All right, so this is what we want. We want to be able to find the arc length function for this curve starting from the point P0, which is given at the ordered pair 1, 2. All right, so take some time, extract what we need, and then we'll move on from here. All right, so let's go through and take what we need. All right, so we're given a function here. So that function that I'm going to be looking at is f of x is equal to 2 times x to the power of 3 halves. There we are. And according to all this, what I want to do is I want to consider this function just to be my function f of t. And the reason for that is because x, we're going to save that variable for x for the actual variable that's going to be able to stop at a certain point in time that we choose. All right, so let's go ahead and let's take this derivative here, f prime of t. So taking this derivative, we're going to have this, that's now going to be 3 multiplied by t, and we subtract 1, so that's going to be a half. Awesome. So now the arc length function, this is going to be our s of x, is going to be the integral from the starting x value. The starting x value, that's going to be 1, so it starts at 1, and it doesn't stop at t, but instead it stops at x. And this is going to be for 1 plus this function, which is 3t to the power of 1 half squared. There we are, and this is dt. Now, in this particular instance, we're then able to simplify this a little bit more, and this is now going to be, for the radicand, 1 plus 9t inside of the square root, and that's dt. Now this turns into a nice u sub. All right. So make a u substitution. Your u substitution can be u is equal to 1 plus 9t, and we'll be able to figure it out from there. All right. So if that's going to be the u sub, then what we're going to have here is going to be that we're going to have, let's see, that's going to be 1 plus 9t, excuse me, and this is going to be to the power of 3 halves multiplied by 2/3. There we are. And then this is also going to be divided by 9, I believe. And let me just double check this derivative really quick. So this derivative, if we multiply by that exponent, that's going to cancel out, gives us 1. That's perfect. That's going to be 1 half. Awesome. Multiply by the derivative of the inside, that's 9, which means we're left with this. Perfect. And that's going to evaluate from 1 to x. It's looking good so far. All right, so this is now going to be 2 over, what's that, 27, I believe? Sure is. 27, there we are. And then this is going to be evaluated from 1 plus 9x, and that's to the power of 3 halves, minus 1 plus 9 to the power of 3 halves, which means this is 2 over 27 multiplied by the quantity of 1 plus 9x to the power of 3 halves minus, and this in here is going to be 10, 10 cubed, and then taking the square root of that is just 10 root 10. There we are. Here's the function. Here is your arc length function. Now, you can try to experiment. Well, let's see if we can try to make some of these, let's see if we can try to find some of these arc lengths. All we have to do now is figure out what the stopping point is. So if we give the interval from 1 to 2, or sorry, if we give the starting point from 1 to 2, and then we create a different starting point, or a different ending point, let's say we want the ending point to be somewhere, I don't know, let's say x is equal to 4. Well, if x is equal to 4, all we do is we substitute it in here into the function, and automatically we'll be able to get this arc length for the interval starting at 1, ending at 4. That's the purpose of the arc length function and how we want to work with that arc length function. All right, so I hope you all enjoyed this lesson, and that's going to be it for arc length. All right, I'll see you all next time.